Okay, today we're going to look at calculations regarding pH, Ka, and the concentration of the H plus ion, which is a proton. So in a previous chapter, when we looked at acids and bases, we looked at what an acid is. So this is one of our common acids, hydrochloric acid. So when we have HCl in our aqueous solution, it dissociates into a hydrogen plus ion and a chlorine ion. So this main compound breaks up into a positive and a negative ion. When we look at this H plus ion a bit closer, it's a hydrogen that has lost an electron. And if you look at the periodic table, you can see that hydrogen only ever has one electron in its normal state. So when it loses that electron, it is now completely positive. So it's essentially a positive charged particle, which we call a proton. So when you see a H plus, it's the same as a proton. And that's where we get the definition of one of our acids, is that it is a proton donor. So you can see that this acid has broken up and it's given away a proton. It's dissociated into a proton. So that's where it gets its name, proton donor. Now we're also going to look at what the pH scale is about. And pH basically stands for the power of the hydrogen ion. So you can see where we're getting the P and the H from there. Now from Junior Cert and from your Leave It Cert studies, you should know that the scale goes from 0 to 14, and in the middle we have 7. So anything below 7 is considered acidic, anything above it is considered basic. Okay, and that is our pH scale. Now what that actually means is that if we break it down, it's to do with the concentration. So anything that you see in closed brackets like this represents the concentration of the hydrogen ion. Okay, pH, the power of the hydrogen ion. So let me just fill in some numbers here. So this scale is to do with the concentration of the hydrogen ion. So the concentration of a solution of pH 7 would have a concentration of the hydrogen ion to be 1 by 10 to the minus 7 moles per liter. And then a solution with pH of 14 will have a concentration of the hydrogen ion to be 1 by 10 to the minus 14 moles per liter. And then over here, we'll have a concentration of the hydrogen ion of 1. Okay, so the hydrogen ion is to do with an acid. So if you look at the progression, it's going from 1 to be very acidic all the way over to 1 by 10 to the minus 14 to be not acidic really at all. Okay, so you're looking at these numbers here. Which one is more acidic? Well, the minus 7, because that's a bigger number, it contains more hydrogen ions. This number over here contains very little hydrogen ions, so it's more basic. And then of course on the other side here we have a very strong acid which contains a very strong, or contains a lot of hydrogen ions, 1 mole per liter over there. So that's where your pH scale comes from, and that's where the numbers also come from 0 to 14. Okay, so to convert basically from our concentration of the hydrogen ion in a solution into a pH, we have this formula here. So we can convert from pH, which gives us a number between 0 and 14, and the concentration of the protons, the amount of protons in the solution. And that should tell us then what the pH of the solution is. So we're going to look at a few calculations that have either we want to figure out the pH or we want to figure out the concentration of the amount of protons in the solution. So we're going to take up a few examples now, and we're going to be using this formula right here. Okay, so there's our question in yellow. We have 3 different ones to calculate, and we are given the concentration of the proton in all of the solutions. So let's look at the first one. We're going to use this formula again. So let's look at number 1. So we need to figure out the pH of the solution, and we're given delta H. So let me fill in my formula. And instead of the H plus, I'm just going to write in the concentration that's given to us. And there we go. So now when you're putting this into your calculator, you need to first write the minus sign, then find a button that looks like log with maybe a filled in square down here, and then an open square. And you can write in on your calculator 10 into the small square to make sure that the 10 is on the bottom, and then sub in this number into that bigger square. When you have all that in and it looks something like that, you just press the equal sign, and you should find that the pH is equal to 2.4 for that example. And let's do the next one. So the pH is equal to minus log to the base 10, 2.62 by 10 to the minus 8. Put that into the calculator again, and we should get 7.58 for the pH. Okay, so the last one was acidic. This one is just above the neutral value and tending towards a basic solution. And we have the last one. Again, just filling it all in. Minus log to the base 10 of the concentration of the hydrogen ion or the protons. Filling all that in, and we should get a pH of 2.28, so acidic. Okay. And you can look at these numbers as well, but these aren't obviously going to give you the accurate pH values. These two tended to be more acidic, and we have a greater amount of hydrogen ions within the solution. And this one has a smaller amount of hydrogen ions with the 10 to the minus 8, and that was tending towards the basic value. Okay, we're going to continue on using this formula. That was converting from the concentration to the pH. Now we're going to convert the opposite way around. So we're going to have the pH, but we're going to try to find the concentration of the hydrogen ion instead. Okay, so we have to find the concentration, and we're given the pHs. So we're going to first of all start with our formula. The pH is equal to minus log to the base 10 of the concentration of the protons in the solution. 5.65 is my pH for the first one. And now to figure out how to actually isolate this hydrogen concentration. So I have to work with my minus log 10 here to try and remove it and isolate the hydrogen ion concentration. So to do that, I have this conversion that minus log to the base 10 of any number, let's say, is equal to x. That can be just a random pH value. That's going to change into the concentration of the hydrogen ion is 10 to the power of minus x. Okay, so that's going to look like this. The concentration of the hydrogen ion is equal to 10 to the power of minus, and our x value here is 5.65. So if you put 10 to the power of minus 5.65 into your calculator, you're going to get the concentration of the hydrogen ion here to be 2.24 by 10 to the minus 6 moles per litre. If you want to pause and try and do the next two yourself, these are a tiny bit harder. Just try and get your head around this conversion here. You can pause now. Okay, the next one. Again, we have our formula. Filling it in. Using our conversion, that the concentration of the proton is 10 to the power of minus 11.15. And for this one, we should get a value of 7.08 by 10 to the minus 12 moles per litre. Okay, and then for the last one, we're going to take 1.09, and the concentration of the H plus is 10 to the power of minus 1.09. And then we put that into our calculator, and we're going to get 0.08 moles per litre for the last one. Okay, so now we're going to look at finding the pH of a solution when we're given the molarity of the solution. So I'm going to write up a few examples. Okay, so let's take a look at the first one. pH of 0.1 molar HCl solution. Okay, so as we know, HCl, if it fully dissociates, is going to dissociate into the single hydrogen ion and a single chlorine ion. Now we know that we have 0.1 moles per litre of the hydrochloric acid, and because the HCl and the hydrogen and the chlorine are all 1:1:1, it's going to have a 1:1 ratio. So we're going to have 0.1 moles of the hydrogen ion produced and 0.1 moles of chlorine ion produced. So that basically just gave us the concentration of our hydrogen ion to be 0.1 moles per litre. So now I can just use my formula up here again straight away, that the pH is the minus log 10 of that concentration which is going to give me an answer of 1. Okay, we want to do the next one. A 0.01 molar solution of H2SO4. So let's look at how H2SO4 might dissociate. We're going to have the hydrogen ion, but we see if there's a 2 here. So if it fully dissociates, it's going to have 2 hydrogen ions dissociated in the aqueous solution, and then a single sulfate ion. Okay, we have 0.01 molar, but this time it's a 1:2:1 ratio. So we're going to have 0.02 moles of the hydrogen ion and 0.01 moles of the of the SO4. So our concentration for the hydrogen ion is 0.02 moles per litre. Okay, so you put that into your formula again, the minus log 10, and then in brackets 0.02. You're going to work out the pH to be 1.7. Okay, the third one, given a mass this time. So we're always dealing with concentration and moles per litre. So we need to convert that grams into moles per litre. So at the moment it's 12.6 grams in 500 centimetres cubed. So to bring that up to a litre, we just need to multiply it by 2. So 12.6 multiplied by 2 is 25.2 grams in 1 litre, or 1,000 centimetres cubed. To convert from mass to moles, we have this formula here. Number of moles equals mass over relative molecular mass. And the relative molecular mass of our nitric acid would be a 1 for the hydrogen, and then it's going to be a 14 for the nitrogen, and 3 times 16 for the oxygen. Okay, so we're going to put the mass, 25.2 of what we actually have, over the relative molecular mass, and that will give us the moles per litre, which is 0.4 moles per litre. Now let's take a look at how the nitric acid will dissociate. Okay, so it's a 1:1:1 ratio. So if I have 0.4 moles of the nitric acid, I will have 0.4 moles of the hydrogen ion as well. So we're going to put that into our formula and into the calculator, and we'll get a pH of 0.4. So now the next one, the fourth one, if you want to give it a go yourselves, you can pause here and try that one. Okay, so again we have mass, so we're going to go 5.8 grams in 250 centimetres cubed solution. Again, we have to bring that up to a litre, so this time we're going to multiply it by 4, and we're going to get 23.2 grams in 1 litre. Again, using our formula, mass over relative molecular mass equals the number of moles. So 23.2 over H2SO4, which is 2 times the 1 for hydrogen, a 32 for the sulfur, and 4 times 16 for all of the oxygens. And that is going to give us a molarity of 0.2 moles per litre for the sulfuric acid. And if we take a look at how sulfuric acid now dissociates, we've already seen that it dissociates into 2 hydrogen ions and a single sulfate ion. If we have 0.2 moles per litre of the sulfuric acid, we can see it's a 1:2:1 ratio. We're going to have 0.4 moles per litre of the hydrogen ion and 0.2 moles per litre of the sulfate. So knowing our concentration of the hydrogen ion, or the amount of protons, we can find out our pH. Put that into the calculator and we're going to get a pH of 0.4. Okay, they were all acids. If we were given a base, we can really just do the same thing. So let's take a look at a base. So if we were to calculate the pH of 0.15 molar sample of NaOH, which is a basic solution, the formula is basically the exact same, except we're going to use P, power of the hydroxide ion, POH instead. And that's going to give us the minus log to the base 10 of the concentration of the OH ion. Now let's take a look at how sodium hydroxide dissociates to a single sodium ion and a single hydroxide ion. If we find the concentration of sodium hydroxide to be 0.15 moles per litre. You can see it's a 1:1:1 ratio. So we're going to get 0.15 moles per litre of the hydroxide ion as well. So we can put that up into this formula. Put that into the calculator and we will get 0.82. Now 0.82 shows that it's almost acidic, but this is not the power of the hydrogen ion. It's the power of the hydroxide ion. So to find the pH, this is the new formula. We're going to take 14, which is the end number of our pH scale, and minus the power of the hydroxide ion. And that will give us a pH of 13.18, which indicates a basic solution. Okay, so we've looked at pH, the concentration of the hydrogen ion, the concentration of the hydroxide ion, and had to convert between the two, and whether if we're given mass, convert into moles, and then using that formula once again. So now we're going to look at another formula, and it's to do with acid dissociation. So we've seen like HCl, that A represents like a Cl or whatever comes out after the hydrogen in an acid, like H2SO4, the A would represent the SO4 part, okay? So let's say it's a single HCl, pretend that it is, and it dissociates into its hydrogen part, and then whatever is left over is represented by the A. So like for example, HCl dissociates into its hydrogen part, and then its chlorine part. Okay, so if we've covered equilibrium, that chapter on equilibrium, we can know that this formula here, the equilibrium constant, Ka, for this one is this an acid, is the concentration of the products, which is our hydrogen ion, and then whatever ion is left over the concentration of our reactants. Okay, so now what this equilibrium constant tells us, if we have all of these concentrations, it tells us how well the acid is in dissociating. Okay, so the higher the Ka value, the better or more likely the acid is at disassociating, which means that it's going to produce more hydrogen ions. So it's going to be a good proton donor, which means it's going to be a strong acid. Okay? So sometimes we are also given that number. Okay, so we're going to look at that now, an example. Now there's two formulas that we need to learn off for this that are not in your log tables. And it's the concentration of the hydrogen ion equals the square root of that equilibrium constant for the acid dissociation times the molarity of the acid. We also have one for basic solutions, which is Kb for base by Mb. Okay, so we're going to take those two and we're going to look at two questions. They're in your book. So the first one, this is question 1, and there's question 2. The dissociation constant, Ka, of methanoic is 1.6 by 10 to the minus 4, and the dissociation constant of ethanoic acid is 1 by 10 to the minus 5, which is the stronger acid. So which is the bigger number? So remember to look up here, 10 to the minus 4, 10 to the minus 5. This is the bigger number, which means that it is better at dissociating, which means we will have more hydrogen ions in the solution, which means it's a stronger acid. So from that, calculate the concentration of the protons in 0.1 molar solution of ethanoic acid, given the dissociation constant. So we need to find the concentration, we have Ka, and we have the molarity of the acid. So we just do a quick sub into the formula. That's our Ka subbed in. Molarity of the acid is 0.1. Quickly put that into the calculator and you will get 1.34 by 10 to the minus 3 moles per litre for that concentration. And that's the answer to question 1. Question 2 then. The pH of a 1 molar solution of ethanoic acid is 2.37. Calculate the hydrogen ion concentration and show the approximate value of the dissociation constant is 1.8 by 10 to the minus 5. Okay, so let me just write out what we have. We have the pH is 2.37. We have the molarity of the acid to be 1 mole per litre. We need to find the concentration of the hydrogen ion, and then we also need to show that Ka is that value up there, but we're not going to use it, so we have to show that at the end. So at the moment all I have is the molarity of the acid, and ethanoic acid is what it is. So if I have the pH, remember I have this formula as well, minus log to the base 10 to give me the concentration of the hydrogen ion. I have the pH, so I can straight away find out the concentration of that hydrogen ion. And remember our conversion then, that the concentration of the hydrogen ion is 10 to the power of minus whatever the pH was. And we will get a value then for the concentration of that protons to be 4.27 by 10 to the minus 3 moles per litre. So that's that part done. Now we need to find Ka. So we're going to go back to this formula. I have the concentration now, I have the molarity of the acid, and I need to find this. So we're just going to sub in. And the molarity of the acid is 1. So 4.27 by 10 to the minus 3 equals the square root of Ka. If you square both sides, you're going to get the value of Ka to be 1.8 by 10 to the minus 5, which is what we have in our question. Okay. And that is that for that video. I hope you found it helpful.